If you've ever been bored sitting around and flipping your phone, you may have noticed that if you flip it a certain way, it does this weird tumbling effect, as you can see in this video. It only works upon this axis. If you flip the phone along any axis besides this one, it just keeps rotating normally. But here you see that as it rotates, it does some sort of tumbling effect. To understand why this happens, we have to first review a few things about angular momentum and what we know about it. And then we'll look at what are called Euler's equations and solve for those equations in order to understand the tumbling effect. In introductory physics, when you learned about rotating objects, you probably looked at symmetrical objects and described their angular momentum as just I omega, where I is the moment of inertia, which is just telling you how the mass is distributed about the object and can be determined from an integral. And omega is oriented along the axis upon which it's rotating. In general, we will be dealing with rigid bodies that aren't symmetrical, and omega here pointing along the z-axis for this arbitrary body has three different angular momentum components. For the z component, when you do r cross p, and r is just the distance vector for individual point particles that make up the mass. When you do that, you get the familiar I omega, but that's just for the z component here. There are also x and y components that won't necessarily be zero because this isn't a perfectly symmetrical object. And this can get even more complicated when you make omega pointing not along any of the three basis axes. You actually get something that can look like this for the case that I had in the picture before. And this is what we define as the inertia tensor. L equals I omega. I is now a very complicated mathematical object. It's no longer the simple L equals I omega with a scalar I. Tensors are in general very complex mathematical objects that are very sensitive to coordinate changes. And the tensors themselves are dependent on your coordinate choice. So if you're measuring in a moment of inertia tensor of a symmetrical cube on its center of mass versus about one of its corners, you will actually get different values. And these tensors change under rotations analogous to how if you change from rectangular to cylindrical coordinates, you have to, for a vector, you have to account for the change of the basis vectors that compose of your vector, even though the magnitude of the vector doesn't change. One thing to note, though, is that we can set up the tensors so that it actually becomes a diagonal matrix, like when we have a symmetric cube rotating about its center of mass. You might get something like this. And when you have a diagonal inertia tensor, the angular momentum vector points in the same direction as the angular velocity. And if you write the L as I omega here, you get I omega equals lambda omega. This becomes an eigenvalue equation in linear algebra terms. And we say that the direction that omega points along is the principal axis, and that there are three of these principal axes for which any body in space can rotate around. And this is always true when you have a diagonal moment of inertia tensor. This will come in handy later when we're trying to solve for the motion of the tumbling cell phone. So coming back to how this explains the tumbling of the cell phone, when we look at the general formula for torque, which is the change in angular momentum in time, we have to do now a product rule because these are now both vectors or tensor matrices. So you get two derivatives here, and we see that even though there's no torque in the system of the flipping phone around the axis that's tumbling, we can tell that I must be changing as well as omega in order for that to occur. And that's obvious when you think about what I said earlier about how I is very coordinate dependent and very sensitive to rotations. I is a function of time. So rather than doing the complicated, doing an I for each moment of time in an arbitrary coordinate axis, we can choose a set of coordinates that are actually co-rotating with the object and create a constant I in time. And we do that by choosing what is called a body frame and create these three principal axes and have a moment of inertia tensor that is diagonal, such that it's diagonal for all time, and these are always orthogonal axes that rotate with the object. This will make that first part of the derivative 0, and we're left with just an omega dot factor here in the torque equation. This changes because now we have to measure the change in angular momentum in this frame as opposed to our measured space frame. This changes the equation from this to this. And Taylor derives that you get this extra factor here, which is true for all rotating reference frames. This explains things like the Coriolis force and the centrifugal force. But written another way, it looks like this. And basically, we have to solve this for the changes in omega in this frame if we want to understand the motion of the cell phone. So in the case that I is diagonal, as we chose with our coordinate axes, you expand it out and you get these three equations here, which are Euler's equations. And these are what govern the motion of the rotating object in that body frame. Basically, we're going to solve these equations using your conditions that torque is 0, and then figure out how omega's components, the angular velocity's components, are changing in time, and then computationally solve that in my simulation. So in the case when torque is 0, we can now take our Euler's equations and rewrite them like this. And we want to solve these now for, I've substituted in the moment of inertias here for the lambdas just so that it's more clear what these are. But we want to solve for these so that we can describe the motion of omega in the body frame. So we have to make one assumption, and that's that when we rotate the object around an arbitrary axis, that it's basically perfectly aligned with that axis. In reality, you'll never have a perfect omega oriented in an axis when you flip an object, because your hand is not going to give it the perfect rotation, right? But you can assume that these are so small that they're basically 0, omega 1 and omega 2. So omega 3 then is constant because of this. When you plug those back in, this just evaluates to 0. So that eliminates this equation, and then we only have these two equations left. And when you take one of them and differentiate it, just to say the first one, and you plug it into the other and you solve, you get something like this. This is basically the most important part of the video and is what describes the tumbling motion. It's saying that the second derivative of one of the components is equal to a multiplicative constant by itself. And we've obviously know this motion is it's familiar to us because when this is a positive constant and you have this minus sign, it's just simple harmonic motion. But there's a key point here. I1, I2, and I3 are not equal to each other. So this won't always be a positive constant. It will be in the case that I3 here is smaller or larger than both I1 and I2. But if in the case where I1 is greater than I3 and I2 is less than I3, we get exponential solutions. This becomes a positive constant in front, and e to the x is the only function that satisfies that differential equation. So this explains why you see the tumbling effect, because you have this exponential increase in omega 1, or whatever the axis is, the intermediate axis, the one where you have a moment of inertia value that is between I3 and I1, and eventually that causes it to tilt away. And that's why it's called the intermediate axis theorem, because it's the axis of the principal axis about which you have the middle moment of inertia, which is kind of the intermediate moment of inertia in that will cause unstable motion. But the other two, the smallest and the largest moments, will not cause unstable motion. So it's a really cool effect to see mathematically. So here we are in the space frame measuring this rotation, and you see that we're getting the tumbling that we see in the video. And I've got two vectors here. The green is the angular velocity, and L is the angular momentum, and red is the angular momentum. And you can see that there are no torques from this frame of reference, so it's constant, which is what we wanted. And the green is doing this weird rotational circulation, which actually lines up with the tumbling motion when you see it from this perspective. It's really cool. But basically these are the basis vectors of the rotating frame, and this is what we use to calculate our moments of inertia about this axis. And then I calculate using the
Euler Equations, how omega changes in that frame, and then I translate it back into the lab frame. I'll show you here just in a second what it looks like when it's in the rotating frame. So here we are in the rotating reference frame, and you can see that now angular momentum and omega are both changing, again according to that second derivative exponential solution. If you were able to see the components, you would clearly identify that one of them is what's causing this change, as it's just kind of going up and over, and it's a very cool motion to describe, and you see that it's periodic, which is cool. And just to prove that it wasn't some sort of preconceived calculation, we can change the rotation axis to be along either the minimum or the maximum, and you see that, well, it's just constant in time. There is no tumbling, as we would expect. And finally, here's a demonstration of this, proving that it's not just limited to rectangular objects that you see here. This is a T-handle aboard the ISS, floating in space where there's no gravity, so there can't be any hidden torques or anything acting on it. You just have it spinning about its intermediate axis, and it's causing this unstable rotation, and it flips back and forth, which is really cool to see. So thanks for watching, and I hope you learned a lot.